Q1 of last year. A 6-person startup chips 14 features in 8 weeks. Everyone is thrilled. The CTO posts on LinkedIn. AI coding tools 10 mstar velocity. Fast forward to Q3. Same team. 0 new features shipped in 11 weeks. 3 senior engineers threatening to quit. The codebase has become what I call a haunted house. Everyone knows something is wrong in there, but nobody wants to open the door. I was brought in as an outside consultant. What I found was not a fluke. It was a pattern I had seen building for months across multiple teams. Functions with 400+ lines and no clear responsibility boundary. Test coverage dropped from 67% to 82%, not because anyone deleted tests, because the AI-generated code was structurally untestable. Cyclomatic complexity scores that would make a 1990s COBOL system blush. And the worst part, every single line of that code looked perfectly reasonable in isolation. That is the trap, and by the end of this lecture, you will have a concrete framework to detect it before it detonates. Now, this is not an isolated anecdote. Let me show you the macro picture, because the timing here is genuinely alarming. In early 2025, Anthropic confirmed Claude Code as a major revenue driver. Estimates placing AI coding tools collectively passed the $2.5 billion annual revenue mark. Cursor, Copilot, Claude, Gemini adoption is at an all-time high. And simultaneously, within the same month, a Hacker News post titled "I'm going back to writing code by hand" hits 98 points and 400+ comments. That does not happen unless a nerve is struck. Developers are not abandoning AI tools because they are lazy or resistant to change. They are hitting walls, maintenance walls, debugging walls, onboarding walls where a new team member looks at the codebase and says, "I have no idea what this is doing or why." The adoption curve and the disillusionment curve are now running in parallel, and the gap between them, that's exactly where technical debt lies. The question is not whether to use AI coding tools. The question is, do you know what you are accumulating? So here is exactly what you are going to walk away with from this lecture. And I want to be specific, because vague promises waste your time. First, a metric-based evaluation framework. 4 measurable signals you can run against any AI codebase today using tools you already have, Radon, Lizard, CoveragePy, or your IDE's built-in complexity checker. No new tooling required. Second, a 5-principle decision matrix, a concrete set of criteria that tells you, per feature type and per team context, whether AI-assisted coding will compound your quality or compound your debt. Not it depends, actual decision branches. Third, pattern recognition. In the next chapter, we will dissect the 6 most common structural anti-patterns that AI code generators produce, so you can spot them in code review before they merge. This lecture is not here to tell you AI coding is bad. It is here to give you the engineering vocabulary and the measurement tools to use it without sleepwalking into a 6-month time bomb. Let's get into it. Let me be direct about who this lecture is for, because if I get this wrong, I waste your time or I talk over your head, and neither is acceptable. This lecture is built for developers with 3 or more years of production experience. You have merged code that broke something at 2 a.m. You have felt the specific dread of touching a module nobody fully understands anymore. You are either a tech lead making decisions about AI tool adoption for your team, or a senior engineer who is already using these tools daily and has started noticing something feels off about the code bases they produce, but you cannot quite articulate what. Or you are an architect who has been handed a code base 6 months after a team went all in on AI generation, and you need a systematic way to assess the damage. If you are a junior developer just starting out, this content will still be valuable, but come back to it after you have felt the pain of maintaining code you did not write. The context makes everything I am about to say land differently. For everyone in that experience bucket, you already know that the hardest bugs are never syntax errors. They are design errors. And that is precisely where AI-generated code has its most dangerous failure modes. Here is the content landscape problem that made me build this lecture. Search for vibe coding or AI coding tools right now. What you will find is overwhelming. Productivity gains, shipping speed records, indie hackers building entire SaaS products solo. That content is not wrong. Productivity is real, at least initially. But it represents one side of a measurement that stops at deployment. Nobody is measuring what happens at month 3, month 5, month 8. The engineering honest analysis, the content that asks what are the long-term structural consequences of this code generation approach, is nearly absent from the mainstream conversation. And the gap is not small. I did a rough content audit for every piece of critical analysis, applying software quality principles, cohesion, coupling, cyclomatic complexity, testability. There are roughly 40 pieces of enthusiastic adoption content. 40-1. That asymmetry is dangerous for the profession. What we actually need, and what this lecture attempts to provide, is a lens built from software engineering fundamentals, not anti-AI evangelism, not uncritical adoption. The kind of structured analysis that asks, under what specific conditions does AI-generated code accelerate quality, and under what conditions does it silently erode it? That question has an answer. And the next chapter starts building it. Alright. Last chapter we watched a production system implode 6 months after an AI-assisted sprint. Now let's do. When I pull up AI vibe-coded repositories, I can usually spot the problem within 30 seconds. And the first thing that jumps out is duplication. Not the obvious copy-paste that any linter catches. I'm talking about near-identical business logic blocks scattered across 5 different service files, each with slightly different variable names, each doing the same validation, the same transformation, the same error handling. The AI didn't reuse your user validator class, it regenerated an equivalent inline, because at prompt time, it had no awareness that the abstraction already existed 3 files away. I've seen a single discount calculation rule duplicated 11 times across a Spring Boot service. 11. When the business rule changed, and it always changes, the developer who inherited that code had to hunt down every copy manually. 3 were missed, caused a billing discrepancy that took 2 weeks to trace. This is pattern 1. Excessive duplication. It's not laziness. It's a structural consequence of how AI models generate code. And it gets worse, because the next pattern is almost the exact opposite problem. So if pattern 1 is AI generating too little abstraction, pattern 2 is the opposite extreme. And honestly, I find this one even more insidious. I call it context-free abstraction. You open a pull request and you see an IUZ repository factory provider strategy interface, a user repository factory provider strategy impl, and an abstracts a repository factory provider strategy base. For a CRUD app with one database, no domain complexity, no future plugin requirement, nothing. The AI generated this because it was trained on enterprise Java codebases, where these patterns exist for legitimate reasons, dependency injection frameworks, pluggable storage backends, complex domain hierarchies. But the AI has zero awareness of whether those reasons apply to your codebase. It pattern matched user repository to this is where enterprise factory patterns live and generated accordingly. What's the real cost? I measured it once during a refactor engagement. A team of 4 developers was spending an average of 22 minutes per feature just navigating the indirection layers before writing a single line of business logic. 22 minutes of cognitive overhead per feature per developer. That's not architecture. That's a maze. And here's the twist. Duplication and over-abstraction can coexist in the same AI-generated codebase. I've seen both in the same file. Now we get to the pattern that genuinely keeps me up at night. Pattern 3. Cosmetic test coverage. Ask an AI to write tests for a payment processing function and it will write tests. Confident-looking tests, with proper method names, with assertions, with mocking setup. And every single one of them will test the happy path. User has sufficient balance, card is valid, network responds correctly, transaction completes. Done. The coverage report shows 78%, looks fine in the CI/DI dashboard, gets merged. What's missing? What happens when the card network returns a timeout after the charge is already posted? What happens when the user's balance hits exactly 0 mid-transaction? What happens when the currency conversion rate is null? I audited 14 AI-assisted repositories last year. Across all of them, the ratio was stark. Happy path tests outnumbered edge case tests by roughly 8 to 1. In human-written test suites from the same on pre-AI code, that ratio was closer to 2 to 1. The AI isn't testing your system. It's performing the appearance of testing your system. And the dangerous part is that your coverage tooling can't difference. Coming up next, I'll show you exactly why the AI's architecture produces all 3 of these patterns. It's not random. It's structural. At this point, some of you might be thinking, okay, but these feel like user error. Better prompts, better instructions, problem solved. I used to think that too, until I started looking at this from the architecture side. These 3 patterns aren't accidents. They are direct, predictable outputs of how large language models are built. Here's the core mechanic. An LLM generates code by predicting the next token based on local context. What it has seen so far in this conversation, this file, this pronto. It is optimizing for local plausibility. Does this next line look like valid code given what came before? It is not asking. Does this decision maintain the global coherence of a 40,000-line code base it has never fully seen? This is why duplication happens. The model doesn't know your abstraction exists outside the current context. This is why over-abstraction happens. It's pattern matching to the statistical average of professional code, which is enterprise code, which uses factories and strategies everywhere. This is why tests lack edge cases. Edge cases require domain knowledge about what actually fails in production. And that knowledge lives in your incidents, your runbooks, your team's heads, not in the training data distribution. Token prediction is brilliant at local syntax. It is structurally blind to global design. That's not a bug they'll fix in the next model version. That's the fundamental trade-off of the architecture. Wait, it gets compounding. Let me show you what happens across multiple sessions. Here's where the compounding damage happens, and this is the mechanism I wish more teams understood. They go all in on AI-assisted development. Consider a typical workflow. Monday, a developer opens a new session to add user authentication. The AI generates it, reasonable, coherent, self-consistent code. Wednesday, a different developer opens a fresh session to add auth integration. That session has no memory of Monday. The AI generates OAuth handling that is also internally coherent, but it makes different assumptions about session management, uses a different error handling convention, introduces a parallel user object model. Friday, a third developer adds email verification. Same story. Now multiply this across 6 months and 20 developers. Every individual AI session was locally reasonably. No single output was obviously wrong. But the codebase as a whole has accumulated 3 different error handling conventions, 2 parallel user models, inconsistent naming across modules, and architectural decisions that directly contradict each other in subtle ways. I call this incremental architectural drift, and it's almost impossible to detect in code review, because each piece looks fine in isolation. The only way to see it is to look at the whole system. When I do architecture reviews on these codebases, I use a dead simple heuristic. If I can't tell which conventions are intentional decisions versus AI generation accidents, the drift is already critical, and that brings us to the real question. What does this actually look like in a concrete before and after comparison? Let's go look at real code. Theory is useful, but I know what actually lands. Seeing the real thing side by side, I'm going to show you a comparison I use in actual code review training sessions. Both sides implement the same feature, parsing and validating an incoming webhook payload, extracting order data, and triggering downstream processing. Left side is from a pre-AI codebase, written by a mid-level developer on the team. Right side is the AI vibe-coded version, generated through a series of Copilot and ChatGPT sessions over 3 weeks by multiple team members. Look at the naming on the right. Parse webhook data, process payload info, handle incoming order object. 3 different naming conventions for the same conceptual operation in the same file. Look at the method sizes. The AI version has one method that does parsing, validation, transformation, and triggering a downstream event. Single responsibility. Gone. Now look at the left side. Extract order from webhook, validate order payload, publish order received. Consistent verb-noun convention. Single responsibility per method. When I ask developers in workshops to estimate how long it would take to add a new validation rule to each version, the average estimate for the human-written version is 4 minutes. For the AI version, it's 26 minutes. Same feature, 6-fold difference in modification cost. And this isn't cherry-picked. It's representative of the pattern I see in roughly 70% of AIV codebases as I audit. Can you learn to spot this in a pull request before it gets merged? Absolutely. Let me give you the checklist. All right. We've classified the patterns. We've explained the structural causes. We've seen them in real code. Now let me give you something immediately actionable. This is the AI code review checklist I hand to engineering teams when they start receiving AI-assisted pull requests. 7 signals. When I see 3 or more of these in a single PR, I block the merge and request a human refactor pass before it goes in. First, naming convention drift. Do methods in this file follow the same naming pattern as the surrounding codebase? Second, abstraction to requirement ratio. Count the interfaces and abstract classes. Does each one map to an actual domain variation that exists today? Third, single responsibility check. Can you describe each method's purpose in one sentence without using the word and? Fourth, test case distribution. What's the ratio of happy path to edge case tests? Below 3:1 is a red flag. Fifth, duplication scan. Run a simple AST-based diff, or even a grep for recurring logic blocks longer than 5 lines. Sixth, context assumption audit. Does the code assume any infrastructure, configuration, or behavioral contracts that aren't documented in this PR? Seventh, cross-session consistency. If this feature spans multiple PRs, do they share the same error handling and naming conventions? This checklist won't catch everything, but it will catch the majority of AI-generated technical debt before it gets committed to your main branch. In the next chapter, we're going to put hard numbers on this, because it feels messier is enough to convince a product manager to slow down. You need metrics, and the data is more alarming than the anecdotes. Let's stop talking in abstractions and start talking numbers. In the previous chapter, we classified the patterns. Now we measure them. Cyclomatic complexity, defined by Thomas McCabe in 1976, counts the number of linearly independent paths through a function. A score of 1 to 10 is considered simple and maintainable. Above 15, you're in high-risk territory. Above 25, peer review becomes nearly impossible. Here's what I found when I ran Radon. That's a Python complexity analyzer across 3 real production code bases where teams have been doing AI-assisted development for 6 months straight. The human-written baseline averaged a cyclomatic complexity of 7.2 per function. The AI-generated functions, they averaged 18.4. That's not a marginal difference. That's a function that has over 2.5 times as many execution paths to reason about, to test, and to debug at 2 a.m. when production is down. The AI isn't writing bad code by accident. It's optimizing for completeness of the prompt response, not for the cognitive load of the next engineer who reads it. And that distinction is everything. But complexity alone is only half the story. What happens when you add coupling into the equation is where things get genuinely alarming. Now let's talk about coupling, specifically afferent coupling, efferent coupling, and the instability metric derived from them. Afferent coupling, Ca, is the number of external modules that depend on your module. Efferent coupling, C, is the number of modules your module depends on. The instability metric I is simply C divided by Ca plus S. A score close to 0 means your module is stable, but potentially rigid. A score close to 1 means it's unstable, highly likely to change, and highly likely to cause cascading breakage when it does. I ran this analysis using Dependency Cruiser on JavaScript codebases and ArchUnit on Java codebases. Look at this table. For human-written modules, the median instability 0.34. For AI-generated modules, it was 0.71. Why? Because AI models don't understand your existing module boundaries. They import whatever library or internal module resolves the prompt most directly. They add dependencies without asking whether that dependency already exists in a wrapper you built. Over 6 months of AI-assisted sprints, teams went from 40 external dependencies to 127. That is a 208% increase in dependency surface area. Every one of those new dependencies is a potential security vulnerability, a breaking change waiting to happen, and a line in your package lock.json that someone will eventually have to explain. And what happens when you overlay these coupling numbers on top of the complexity numbers over time? That's where the data becomes genuinely uncomfortable. And here's the part that surprises even experienced engineers. Damage isn't linear. It's a compound curve. Let me walk you through this timeline. At month 1, your AI-assisted team looks like heroes. Velocity is up. Tickets are closing fast. Complexity scores are only slightly elevated, maybe 9.1 average versus the 7.2 baseline. At month 2, complexity climbs to 11 to 11.8, and coupling instability is starting to show in integration test failures. You start adding workarounds. Each workaround, largely written with AI assistance, adds more complexity. At month 3 you hit what I call the first inflection point. The metrics start compounding on each other. A highly coupled module with high complexity breaks. You ask the AI to fix it. The fix adds another import and another conditional branch. By month 4, average cyclomatic complexity has crossed 16, and your sprint velocity starts dropping despite identical team effort. By month 5, you're spending more than 40% of each sprint on bug fixes and unexpected breakage. Month 6 is when the CTO calls a meeting and asks why the team is slower than before they adopted AI tools. And nobody in the room has a quantitative answer ready, because nobody was measuring. The lesson isn't that you should avoid AI tools. The lesson is that you cannot fly blind. Instrument your codebase from day one, and the next section will show you exactly what framework to use. When you go to management and say the AI-generated code has quality problems, the first thing they ask, can you prove it? And that's a fair question. Gut feelings and war stories don't survive a budget meeting. You need a framework with teeth. ISO 55010, the international standard for software product quality, gives you exactly that. It defines 8 top-level characteristics: functional suitability, performance efficiency, compatibility, usability, reliability, security, maintainability, and portability. For AI-generated code, 4 of these are where the failure modes cluster most aggressively. Maintainability is hit by the high complexity and coupling we just measured. Reliability is compromised by the shallow edge case handling we saw in Chapter 2's pattern analysis. Security takes a direct hit because AI models frequently reproduce vulnerable patterns from their training data. We're talking about SQL injection patterns, hard-coded credential patterns, missing input sanitization, and performance efficiency suffers because AI-generated code frequently optimizes for correctness of the first test case, not for production load profiles. The power of ISO 25010 is that it's not my opinion. It's an internationally recognized standard that your CTO, your team, and your external auditors all recognize. When you map your complexity scores, your test results, and your security scan output onto ISO 25010 characteristics, You're no longer having a technical argument. You're producing an engineering audit. And in the next scene, I'll show you the test that makes that audit deeply uncomfortable reading. Now here is the single most dangerous number in AI-assisted development, 80% line coverage. I've seen teams look at that number and declare their AI-generated test suite is production ready. I've also seen those same teams get woken up at 3 a.m. by incidents that those tests completely missed. Here's why line coverage is a lie when used in isolation. Line coverage tells you whether a line was executed during the test run. It tells you nothing about whether it was executed with the inputs that actually matter. Branch coverage is harder to hit. It requires you to exercise every conditional branch, both true and false. And mutation testing, which tools like PIT for Java and MutMut for Python perform, is the real stress test. A mutation tester makes small changes to your production code. It flips a greater than to a less than, it removes a null check, and then reruns your test suite. Your tests don't catch the mutation, your tests aren't actually guarding that logic. Look at this data from the same 3 codebases. AI-generated test suites averaged 81% line coverage. Sounds good. Branch coverage? 54%. That's a significant gap. But the mutation score, the percentage of mutations caught, was only 38%. That means 62% of logical errors introduced into the codebase would survive the test suite entirely. Human-written test suites in the same codebases showed 76% line coverage, but 71% branch coverage, and 64% mutation score. Lower headline number, dramatically better actual protection. The metric you're being shown is not the metric that matters. And in the next scene, I'll show you how to package all of this into a report your management chain cannot dismiss. So you have the complexity numbers, you have the coupling data, you have the coverage gap. Now you need to turn all of that into something a non-technical stakeholder will act on. This is where ISO 25010 becomes your organizational weapon. Here's the scoring approach I use in practice. For each of the 4 high-impact quality characteristics, maintainability, reliability, security, performance efficiency, you assign a score from 1 to 5 based on objective metric thresholds. Maintainability score. Cyclomatic complexity average below 10 scores a 5, above 20 scores a 1. Reliability score. Mutation test score above 70% scores a 5, below 40% scores a 1. You populate each cell with your actual measurement data and the tool that produced it. The result is a quality scorecard that is traceable, reproducible, and audit-ready. When you hand this to a CTO or a compliance officer, they cannot say that's just your opinion. The metrics are sourced from industry-standard tools. The thresholds are derived from ISO 25510 and empirical research. The scoring is deterministic. I've used exactly this format to successfully justify a 2-sprint refactoring hold on 3 separate occasions, which is something your subjective gut feeling will never get you. The next chapter shifts gears. We've looked at the numbers. Now I'm going to tell you the stories behind the numbers, because 25 years of debugging other people's messes has shown me things the metrics alone can't capture. Engineers love metrics. Businesses love money and time. Walking into a budget meeting with cyclomatic complexity scores and mutation test percentages, you will get politely ignored. You need to translate. Here's the translation I've proven works. Every 1-point increase in average cyclomatic complexity above the baseline of 10 correlates to approximately a 6% increase in mean time to implement a new feature. That's not a theoretical estimate. That's derived from DORM metric data collected across those same 3 codebases I've been referencing. At a complexity average of 18, you're looking at a 32 to 48% increase in feature lead time compared to a well-maintained baseline. Now say your team has 6 engineers at an average fully loaded cost of $50 per year each. A 40 reduction in effective velocity is costing you the equivalent of 2.4 engineer years annually. That's $3 a year in hidden productivity loss. Not in server costs, not in tooling. In the salaries you're already paying for people who are now spending nearly half their time fighting the complexity, coupling your AI tools created. The AI coding tool probably costs you $1 per seat per month. The technical debt it generates could cost you $3 a year in lost velocity. That's the productivity paradox, and there's a way to put an even sharper number on the future cost, which I'll show you right now. The final piece of the quantification puzzle is treating technical debt as what it actually is, a loan with compound interest. Here's the formula I use, and I want you to write this down because this is the one thing from this entire lecture that you can put in a slide deck tomorrow. Technical debt future cost equals current remediation cost multiplied by E raised to the power of the interest rate times time in months. In practice, I use a simplified discrete version. Each month you don't address the debt, the remediation cost grows by 15 to 25% due to increased interdependencies, lost context, and team turnover. If your current codebase needs 40 engineer days to refactor to a healthy complexity baseline, and that's a real number from a real audit I ran 14 months ago, waiting 6 months at a 20% monthly compounding rate means that 40 days becomes 120 days. You tripled your refactoring cost by waiting half a year. Waiting 12 months, you're looking at 3071 engineer day the same codebase. That's nearly 2 engineer years of remediation work, or for it could have been addressed for 40 days at the 6-month mark. This is not hyperbole. I've lived this calculation on 3 separate engagements. The formula gives you a number you can put in front of a CTO and say, a month we delay this refactoring costs us X additional engineer days. That conversation changes decisions. In the next chapter, we'll go behind the numbers, 25 years of war stories that show you exactly what these metrics like when they become production incidents, team burnout, and emergency board calls. Let me tell you about a team I was brought in to rescue. 4 months into a greenfield project, fully AI-assisted, they had had working software, demos that impressed stakeholders, and a codebase that looked clean on the surface. Then their senior dev went on parental leave, and they needed to onboard a replacement. That's when everything collapsed. Nobody, not the CTO, not the remaining engineers, could answer the question, why does this module do this? The AI had generated working code, but the intent, the trade-offs, that we decided against approach B because of X, none of that existed anywhere. There were no commit messages with reasoning, no AD errors, no comments explaining decisions, just code that worked until you needed to change it. I call this knowledge debt with no principle. It's debt you can't even audit because the original borrower was a language model with no memory. Metrics won't show you this. Your static analysis tools won't flag it. But the moment you need to grow the team, you will feel it like a wall. And what I found next inside that codebase made the knowledge problem look minor by comparison. The second incident is the one that keeps security engineers up at night. A mid-sized SaaS company, multi-tenant architecture, and an AI-generated authentication flow. Here's the thing, it passed code review. It passed their automated security scans. Passed penetration testing. The logic looked textbook. JWT issuance, token validation, proper expiry. Everything you'd want to see. But there was a subtle flaw baked into session invalidation under a very specific edge case. When a user from tenant I initiated a password reset, at the exact moment a concurrent login from a separate session was in flight, the invalidation logic contained a race condition that could, under the right timing, allow the old session token to remain valid for up to 15 minutes after reset. In a single tenant app, the blast radius is 1 user. In a multi-tenant SaaS, an attacker who knew the pattern could systematically exploit it across accounts. The AI had generated code that was contextually correct in isolation. It had no understanding of the multi-tenant invariance the system relied on. It saw the limit was shown, not the system it was operating in. This is what I call context blindness, and no linter in the world catches it. Now, let me show you the third story, because this one hits your budget directly. Third story. A team comes to me with a refactoring project. Their AI-assisted codebase had grown for about 8 months, and they needed to extract a billing module into a separate service. Their estimate, 2 weeks. I looked at the codebase for 2 hours and told them, budget 4 months, minimum. They didn't believe me. Here's what AI-generated coupling looks like at scale. Because AI models optimize for making each individual feature work, they reach across module boundaries constantly. The billing logic had direct database calls into the user session table. The notification service was importing billing constants. The API gateway was doing currency formatting that belonged in billing. It wasn't architectural laziness. The AI just grabbed whatever was in context to make each prompt put function correctly, with zero regard for where that logic actually belonged. By month 2 of refactoring, we had found 47 distinct cross-module dependencies that weren't in any diagram. By month 4, we shipped. The original 2-week estimate was off by a factor of 8, and the downstream lesson here is critical, because the same pattern is quietly forming in your codebase right now, even if you can't see it yet. In the next section, I'm going to talk about the consequences that teams are too embarrassed to admit publicly. Now, I want to talk about something that makes developers uncomfortable, because it feels like a personal failure. After 6 months of heavy vibe coding, I've watched engineers, genuinely talented engineers, lose the ability to debug effectively, not because they got lazy, because the muscle atrophied. Think about what debugging actually demands. You form a hypothesis about system behavior, you reason about state at a specific execution point, you trace causality backward from a symptom to a root cause. That is a skill that requires constant exercise. When AI handles code generation end-to-end, and the developer's job becomes prompt writing and acceptance testing, those debugging muscles go unused for weeks at a time. I had one engineer, 5 years of experience, who came to me 6 months into an AI-heavy project, completely unable to set a breakpoint and reason through a stack trace without asking the AI to explain it first. He wasn't incompetent. He had outsourced his reasoning loop so completely that no longer ran independently. And here's the part nobody puts in their conference talk. This isn't just about that one engineer. It's a team-level capability regression. When a production incident hits at 2 a.m. and the AI tool is rate limited or context is too large to load, who debugs it? The team that can no longer debug without assistance. But the skill atrophy problem has a twin. And the twin is organizational, not individual. The organizational twin of skill atrophy is what I call review theater. Here's how it happens, and I've seen it in 3 separate companies across different industries. AI starts generating code fast. Velocity go up. Stakeholders are happy. But code volume per sprint doubles, then triples. The PR queue grows. Reviewers are still human. They still have the same 24 hours in a day. So what happens to review quality? It degrades systematically. First, reviewers skimming AI-generated PRs because they look clean and consistent. Then they start rubber stamping them because the AI generated it probably fine. Within 3 months, code review becomes a compliance checkbox, not a quality gate. I benchmarked this in one team. Average review time per PR dropped from 47 minutes to 11 minutes over 16 weeks, while PR size grew by 3%. The math is brutal. You're doing less review per line of code precisely when the code most needs scrutiny, because AI-generated code carries all the subtle flaws we've been discussing. The compare here is stark. A team that reviews AI output, like human output, catches the context blindness and coupling issues. A team that reviews AI output like its pre-validated infrastructure catches nothing. And when you stack skill atrophy on top of review theater, you get a compounding failure mode that no metric dashboard will surface until you're already in the war story. I'm about to hand you a framework to avoid. In the next chapter, I'll give you the 5 principle decision framework for exactly where AI coding is safe and where it is structurally dangerous. All right. After 25 years of watching Codebase's age, some gracefully, most not, I've dissed everything into 5 principles, not opinions, principles backed by failure data. Let's start with principle 1, because this is where most teams get it completely wrong from day one. They treat all code as equally safe for AI generation. It is not. There is a hard boundary, and you need to draw it explicitly before your first AI-assisted PR gets merged. On the left side, the green zone, you have scaffolding, boilerplate, cured endpoints, DTO mappings, migration scripts, and test fixtures. These are structurally repetitive, low-entropy patterns. AI excels here because stakes are immediately visible and easily corrected. On the right side, the RED zone, you have your core domain logic, security boundaries, concurrency control, distributed transaction coordination, and state machines. AI-generated code is statistically subtly wrong in ways that won't surface for months. I've seen a payment service go down because an AI-generated state machine had a valid-looking but logically incorrect transition for a partial refund edge case. The code reviewed clean. The tests passed. The bug waited 6 months to surface in production. Draw the boundary. Write it down. Enforce it. The next principle explains WHO enforces it, and that answer might surprise you. Principle 2 sounds obvious until you see it violated in a real PR review. The rule is simple. Every single piece of AI-generated code must a named human engineer who can walk into a conference room with no laptop, no AI tool open, and explain out loud why this component is designed the way it is, not what it does, not why it was designed that way. This is the ownership test, and I promise you if you run this test on your team right now, at least 30% of your AI-rated modules will fail it. The engineer will say something like the AI suggested it, and it seemed to work. That is not ownership. That is abdication. The moment architectural decision authority transfers from a human brain to a probabilistic text model, you have created an unknown component. Unknown components are the ones that nobody wants to touch when they break at TAM. They are the ones that accumulate the most irrational workarounds. Principle 2 mandates that AI assists and humans lead, always. AI is the junior developer who writes a first draft. The senior engineer, your named owner, must be able to defend every design decision as if they wrote it themselves. Here is what this looks like in practice, and I'll show you the matrix next. Here is the practical artifact that makes principles 1 and 2 real inside your team. This is the ownership matrix. 4 columns: code category, AI involvement level, named owner requirement, and review depth standard. Read it top to bottom. This is your governance document. For infrastructure as code and boilerplate, AI can generate freely, a team-level owner is sufficient, and a standard peer review is acceptable. For API contracts and data models, AI can draft, but a senior engineer must approve the schema. Because schema changes are some of the most expensive mistakes to undo in distributed systems, I've seen a single nullable field become a 6-week migration nightmare. For domain services, AI is limited to generating test stubs only, a named domain expert is required as owner, and a full architecture review is mandatory before merge. For security and auth modules, AI involvement is prohibited. Full stop. 1 human author, 1 security reviewer, 0 AI-generated lines. I know that sounds extreme. I've seen what happens when it's not enforced. A CWE 287 authentication bypass shipped to production because an AI-generated token validation silently accepted malformed JWTs. 0 exceptions on security. Print this matrix, put it in your team wiki, and make it the first thing a new engineer reads. In the next section, we move from who owns the code to how we verify it's actually good, and the specific numbers that should trigger automatic rejection. Principles 1 and 2 define a human accountability. Principle 3 is where we get mechanical, and I mean that literally. We stop relying on human judgment alone, and we encode quality standards into the pipeline itself. Because here is the brutal truth I learned from a financial services client 2 years ago. Human reviewers are systematically bad at complexity problems in AI-generated code. The code looks reasonable. It is organized, it has docstrings, variable names are sensible. But underneath, the cyclomatic complexity is 24 when your threshold is 10. The efferent coupling is off the charts. Branch coverage is 34% on a module that handles money. These are not subjective opinions, they are measurable numbers that predict future maintenance cost with statistical significance. So here are your non-negotiable numeric gates. Cyclomatic complexity per function, maximum 10. If an AI-generated function exceeds this, the PR is automatically rejected. No exceptions, no manual override without a documented ADR. Efferent coupling instability index, maximum 0.7. Above this, the module is too dependent on volatile abstractions. Branch coverage for domain code, minimum 20%. For anything touching payments, auth, or data integrity, minimum 20%. Cognitive complexity, this is the SonarQube metric, not cyclomatic, maximum 15. I added cognitive complexity after I noticed AI code that passed cyclomatic thresholds, but was still nearly unreadable due to deeply nested conditionals. The next tool slide shows you exactly how to wire these into your pipeline. But first, ask yourself, do you even have these thresholds defined today? If not, that is your most urgent action item from this entire lecture. Principal car addresses a failure mode I see on almost every team that starts using AI coding tools heavily within the first 3 months. I call it incremental drift compounding. Here is how it works. Day 1, AI generates a module that is slightly messier than your standard. It passes review because we'll clean it up later. Day 3. The next AI builds on top of that messy module, inheriting and amplifying its structural problems. Day 7, you now have 2 layers of drift, and the third AI session is using both as context. So it generates code that is consistent with the drift, not with your actual standards. By week 4, you have a coherent-looking mess that is internally self-consistent, but systematically misaligned with your codebase conventions. Principle 4 breaks this cycle with one rule. AI-generated code must be refactored to meet ALL quality gate standards before the next AI session begins on that module. Not before the sprint ends. Not before the release, before the next session. This sounds aggressive. It is aggressive. But the math is unambiguous. A 20-minute refactor session on day 1 saves you a 3-week extraction project on month 6. I've done both. I know which one I prefer. The tight feedback loop is not a nicety. It is compound interest working in your favor instead of against you. Here is the toolchain that makes this feedback loop fast enough to actually in practice. Let me show you the actual toolchain. Because principles without automation are just wishful thinking. I've seen teams with beautiful coding standards documents and 0 enforcement. Within 6 months, those documents are folklore. You need gates in the pipeline that do not care about deadline pressure, manager urgency, or just this once exceptions. The stack I recommend is layered, and I want you to think about it top to bottom as your quality signal propagates from the developer's machine all the way to the merge gate. Layer 1 is your local development environment. Configure your IDE with SonarLint or a language-specific linter. The developer sees complexity warnings before they even commit. Layer 2 is pre-commit hooks. Use a tool like pre-commit with Lizard for cyclomatic complexity checks. The commit is blocked if thresholds are exceeded. No bypass without explicit override with a reason. Layer 3 is your CI pipeline. Run full SonarQube analysis on every PR. Wire the quality gate status as a required check. The PR be merged if SonarQube quality gate fails. Layer 4 is your PR bot. Configure a bot that posts a complexity and coverage summary directly in the PR comment thread, with specific failing functions highlighted. This makes the data impossible to ignore. The key insight here: each layer catches drift earlier and at lower cost. Catching a complexity violation on SonarLint costs 10 seconds. Catching it in a production incident costs weeks. This toolchain is not theoretical. I have it running in 3 different client codebases right now. The 5th principle is the one nobody wants to hear, and it is arguably the most important one for your long-term engineering capability. This is the principle that gets the most pushback in every workshop I run. Not because engineers disagree with the logic. They don't. It's because it requires something AI tools have conditioned us away from: sustained manual effort with no immediate productivity shortcut. Principle 5 is the deliberate practice counterweight. Here is the problem it solves. After 12 to 18 months of heavy AI-assisted development, your engineers begin to lose the ability to perform deep debugging without tool assistance. Not because they are bad engineers, because debugging, like any complex cognitive skill, requires regular, unassisted practice to maintain. Think of it like a surgeon who switches to robotic-assisted procedures exclusively. The robot is more precise for routine work, but when the robot fails mid-operation, and eventually it does, you need a surgeon who can operate manually. I have personally witnessed a senior engineer, 8 years of experience, unable to trace a production memory leak without AI assistance, because the last time she had done unassisted heap analysis was 14 months earlier. Principle 5 mandates deliberate manual coding on critical path modules regular intervals. Specifically, at least one critical path module per quarter must be written entirely by hand. No AI autocomplete, no AI code generation. The engineer writes it, reviews it, debugs it, and tests it manually. This is not about distrust of AI. It is about maintaining the engineering craft that allows you to judge AI output, debug AI-generated failures, and make architectural decisions that AI cannot make for you. Your debugging capability is a perishable skill. Treat it that way. Now let me show you how all 5 principles fit together into a single decision framework your team can start using tomorrow. Now we bring all 5 principles together. I want you to have a single artifact you can hand any engineer on your team and say, "This is our AI coding policy." Not a 40-page governance document nobody reads. A decision matrix that fits on one slide. At the center, every AI coding decision. Branching left, the boundary and ownership questions, principles 1 and 2. Is this code in the safe zone? Yes. Proceed with AI. No. Human written only. Does this component have a named owner? The white test. Stop and assign 1 before generating a single line. Branching right, the quality and feedback questions, principles 3 and 4. Do all quality gate metrics pass within this session? Refactor now, not later. Is this a new session starting on a previously AI-generated module? Yes. Run quality checks on the existing code first, before generating more. And at the top and bottom, Principle 5, the quarterly manual coding requirement runs orthogonal to all other decisions, enforced on a calendar schedule regardless of project state. This mind map is not just a summary. It is a decision tree. Print it, post it in your team Slack, add it to your PR template as a checklist header. The teams I work with that have an explicit, written policy like this show measurably different outcomes at the 6-month mark. Lower complexity drift, higher coverage retention, and critically, faster incident resolution, because engineers retain their debugging skills. One more thing before we close this chapter. I want to show you how to actually roll this out without blowing up your current delivery commitments. The last thing I want to leave you with before we move into your action plan is a realistic rollout sequence. Because I have seen teams try to implement all 5 principles simultaneously on week 1, and then abandon all of them by week 3, because the organizational change load was too high. Do not do that. Here is the 90-day phased rollout I recommend. Days 1 through 30, foundation phase. Do 2 things only. First, define your principle 1 boundary map for your specific codebase. Write down which modules are safe and which are dangerous. Second, assign named owners to every existing AI-generated module. Just these 2 actions more risk than most teams expect, and they require 0 tooling changes. Days 31 through 60, gate phase. Implement the principle 3 quality gates in your CI pipeline. Start with complexity and coverage thresholds. Configure SonarCube. Wire the quality gate as a required PR check. Run it in warning mode for the first 2 weeks, then switch to blocking mode. This gives your team time to calibrate without immediate delivery disruption. Days 61 through 90, culture phase. Introduce principle 4 tight feedback loops as a team norm. Schedule the first principle 5 deliberate practice sprint. 1 week. No AI tools, full team visibility. Make it a shared learning event, not a punishment. By day 90, all 5 principles are active. Not perfectly, but actively. And here is what the next chapter delivers. The specific action items and decision scripts you take out of this room today so that Monday morning you know exactly where to start. Do not miss that. It is the difference between nodding along to a framework and actually changing how your team works. All right. 5 chapters in, you've seen the day in the war stories, and you've got the 5 principle framework in your head. Now let's make this actionable. No fluff, just the list you can pin to your team's Confluence page starting Monday. The DO list. First, use AI to generate boilerplate and scaffolding. DTEOs, repository interfaces, test fixtures, anything with zero business logic and will hack into coverage requirement. That's a safe zone. Second, use AI for first unit tests on pure functions. Let it write the happy path cases, then you write the edge cases. That division of labor actually works. Third, use AI in pair mode. You write the interface contract first, then ask AI to implement against it. Interface first is the key discipline here. Fourth, always run your static analysis and linting gate on AI output before it touches a PR. Treat AI output like you treated your dev's first commit. It needs review, every single time. These 4 workflows share one common trait. A human engineer stays in the decision seat. The next scene shows you exactly what happens when that human steps away. Now the done list, and I want you to feel the weight of each one of these, because every item here maps directly to a failure mode we dissected in Chapter 4. Don't let AI touch cross-service transaction logic. Remember the payment saga we looked at? The AI-generated compensation handlers had no idempotency keys. That was a Sunday 3 a.m. incident. Don't accept AI-generated SQL that joins more than 3 tables without explaining the execution plan to the reviewer. I've seen AI produce query plans with full table scans on 50 million row tables that looked completely reasonable in code review. Don't use AI to refactor code it didn't originally understand. Feeding it a 2,000-line legacy class and asking it to clean this up produces a confident-sounding rewrite that subtly changes behavior. That's how you get regressions with no paper trail. And the hardest one to enforce culturally, don't skip the ownership assignment because the AI wrote it. That logic is how you end up with modules nobody understands 6 months later. The anti-pattern isn't the tool, it's the abdication of engineering judgment. And that judgment is exactly what makes you irreplaceable in an AI-accelerated world. 3 concrete things. This week. Not next sprint, not next quarter. This week. Step 1. Pick one AI-generated module that's already in your production codebase. Run the metric snapshot we built in Chapter 3. Cyclomatic complexity, cognitive complexity, coverage percentage, and coupling score. Write those numbers down. That's your baseline. If you don't measure, you can't manage. Step 2. Take that module and run it through the ownership matrix from Chapter 5. Ask, does a human engineer know why every decision in this file was made? If the answer is no for more than 30% of the decision points, that module is a liability, and you need to schedule a review session now before it becomes the module everyone is afraid to touch. Step 3. Add one quality gate to your CI/CD pipeline. 1. Start with cyclomatic complexity threshold. Anything over 15 per function fails, build. That single gate, consistently, will catch the most dangerous AI-rated patterns before they reach production. 3 steps, 1 week, measurable outcomes. That's how engineering discipline actually gets built, not in architecture meetings, but in pull request pipelines. Here's the engineering verdict. And I want to be precise, because the internet is full of takes that are either AI is going to replace all developers or AI-generated code is garbage. Both are wrong, and both are useless to you as a practitioner. The truth, based on what I've seen across dozens of codebases and 6 months of post-AI adoption forensics, is this: AI coding tools are force multipliers, but only for engineers who maintain quality discipline. For those engineers, AI genuinely compresses the distance between a well-defined problem and a working solution. It handles the mechanical, the repetitive, the well-trodden. That's real leverage. But for teams that treat AI as a shortcut around engineering judgment, around ownership, around testing, around understanding what the code actually does, AI becomes a slow-motion disaster accumulator. The technical debt doesn't announce itself. It compounds quietly, module by module, until the code base becomes the thing everyone is afraid to change. The tool is not the variable. Your engineering discipline is the variable. That has always been true, and AI has simply made it more consequential. Let's close with the full picture. In this lecture, you learned to classify AI coding risk using the 4-pattern taxonomy. From safe scaffolding, all the way to dangerous autonomous architecture. You got the 3-metric snapshot framework, cyclomatic complexity, test coverage delta, and coupling score, your objective lens for measuring AI-generated code quality over time. You saw Chapter 4's case studies, showing exactly how the degradation curve plays out over 6 months in real production systems. You got the 5-principle framework for deciding where AI is versus where it is genuinely dangerous. And today, you got the deodont list and the 3 this week action items you can execute before your next stand-up. The single most important thing before you close this video, go find one AI-generated module in your codebase right now and ask yourself, if the engineer who prompted this left the company tomorrow, could anyone else explain why every line exists? If the answer is no, you already have technical debt. The question is only whether you're going to address it proactively or wait until it addresses you. Thank you for staying for the full lecture. Now go measure something.